Did you know that the sun can unleash storms that dwarf anything we experience on Earth? These aren't your typical thunderstorms, but colossal tempests born from the sun's fiery heart, capable of sending shockwaves across the solar system. Imagine the sun as a colossal power plant. It's not just the source of light and warmth, it's a dynamic and turbulent sphere of nuclear reactions. Sometimes, this celestial giant experiences massive surges of energy. These aren't mere flickers of light or gentle solar breezes, but powerful eruptions known as solar flares and coronal mass ejections, CME. When these eruptions occur, they can release billions of tons of plasma and magnetic fields into space. These solar tempests travel through space, and when they reach Earth, they interact with our planet's magnetic field, causing phenomena known as geomagnetic storms. But what exactly happens during these interactions? How do they affect our planet and the technology we depend on? Let's embark on a journey to explore how these solar tempests affect our planet. We'll delve into the science behind solar flares and CMEs, understand their impact on Earth's magnetic field, and uncover the effects they have on our ionosphere, satellites, and even our daily lives. Join me as we unravel the mysteries of space weather and its impact on Earth. In the vastness of space, our sun is a constant bustling hub of activity. Among its many spectacular phenomena are solar flares and coronal mass ejections, CMEs, two of the most dramatic expressions of the sun's power. Solar flares. Solar flares are intense bursts of radiation emanating from the release of magnetic energy associated with sunspots. These flares are the sun's way of rearranging its magnetic field lines after they've become twisted and tangled over time. When the tension becomes too great, the lines snap and reconnect, releasing energy in the form of light and heat. Coronal mass ejections, CMEs. CMEs are massive bubbles of gas threaded with magnetic field lines that are ejected from the sun over the course of several hours. They can release billions of tons of coronal material and carry an embedded magnetic field that is stronger than the background solar wind interplanetary magnetic field. IMF strength. CMEs travel outward from the sun at speeds ranging from slower than 250 kilometers per second to as fast as near 3,000 kilometers per second. When these colossal clouds of plasma reach Earth, they can trigger the most powerful geomagnetic storms. The interaction of these storms with Earth's magnetosphere can lead to beautiful auroras, but also pose risks to satellites, power grids, and communication systems. As we continue to explore the intricacies of solar flares and CMEs, we gain not only a greater understanding of our celestial neighbor, but also the delicate balance of forces that govern our solar system. As we venture further into the domain of space weather, let's turn our attention to the solar wind, a stream of charged particles released from the upper atmosphere of the sun. This solar wind carries with it the magnetic field of the sun, known as the Interplanetary Magnetic Field, IMF, and it plays a crucial role in shaping the space weather conditions we experience. Analysis of Geomagnetic Index (SYMH) responses. The Geomagnetic Index (SYMH) is a measure of the horizontal component of Earth's magnetic field. It's sensitive to the solar wind's influence and is used to assess the intensity of geomagnetic storms. When solar wind parameters fluctuate, the SYMH index captures these changes, providing us with a snapshot of the ongoing space weather conditions. Studies have shown that the SYMH index responds to various solar wind parameters such as the solar wind speed, V, dynamic pressure, P, and the southward IMF, BZ, component. These parameters can influence the development of geomagnetic storms, which are disturbances in Earth's magnetosphere caused by these solar activities. Impact of solar flares and CMEs. Solar flares and coronal mass ejections, CMEs, can significantly impact solar wind conditions. They can increase the solar wind speed and dynamic pressure, leading to more intense geomagnetic storms. The relationship between these solar events and the SYMH index is complex, but research has found strong correlations. indicating that solar flares and CMEs are key drivers of space weather events. As these solar wind parameters interact with Earth's magnetic field, they can cause variations in the SYMH index, signaling the onset of geomagnetic storms. These storms have the potential to affect satellite operations, GPS navigation, and even power grids on Earth. By understanding the solar wind parameters and their impact on the SYMH index, scientists can better predict space weather events and prepare for their potential effects on our technology-dependent society. Impact on Earth's magnetic field. The Earth's magnetic field, an invisible shield that protects our planet from the harsh solar wind, is a dynamic and responsive force. It's not a static barrier but a complex system that reacts to external pressures, particularly those exerted by the solar wind and the interplanetary magnetic field, IMF-BZ component. Ground geomagnetic field, H component, response. The horizontal component of the Earth's magnetic field, known as the H component, is particularly sensitive to changes in the solar wind and IMF-BZ when the solar wind intensifies, carrying with it a southward-oriented IMF-BZ. It can compress the Earth's magnetosphere and induce currents in the ionosphere. These currents, in turn, affect the H component readings observed at ground stations. Data from low-latitude stations. Low-latitude stations provide valuable data for understanding the global impact of space weather events. These stations have recorded variations in the H component that correlate with changes in solar wind parameters, offering insights into the extent of geomagnetic disturbances. For instance, a sudden southward turn of the IMF-BZ can lead to a corresponding dip in the H component, signaling the onset of a geomagnetic storm. By analyzing data from these stations, scientists can trace the influence of solar activities on Earth's magnetic field. This knowledge is crucial for predicting geomagnetic storms and mitigating their effects on our technology-dependent world. Effects on Earth's ionosphere. When we gaze up at the clear blue sky, it's hard to imagine that above us is a layer of Earth's atmosphere that is constantly being bombarded by solar radiation. This layer, known as the ionosphere, plays a crucial role in radio communication and satellite navigation. But what happens when the sun, our star, throws a tantrum? Influence of solar flares on the ionosphere's D and E layers. Solar flares, particularly M and X-class flares, are like colossal firestorms on the sun's surface that release a tremendous amount of energy into space. This energy, in the form of increased X-ray and extreme ultraviolet radiation, can reach the Earth's ionosphere within 8 minutes. When it does, it causes a sudden and intense increase in ionization, especially in the lower ionosphere D layer, which lies about 60 to 90 kilometers above Earth's surface. The D layer is usually weakly ionized and has little effect on radio wave propagation. However, during solar flares, the increased ionization can cause high-frequency radio waves to be absorbed rather than reflected, leading to disruptions in radio communication. The E layer, situated above the D layer at about 90 to 120 kilometers altitude, also experiences enhanced ionization. This can affect the propagation of radio waves that depend on this layer for reflection back to Earth. Focus on M and X-class flares. M-class flares are medium-sized. They can cause brief radio blackouts that affect Earth's polar regions. X-class flares, on the other hand, are the largest and most powerful flares. They can cause planet-wide radio blackouts and long-lasting radiation storms. Understanding the impact of these flares on the ionosphere is not just about knowing the what, it's about unraveling the why and how. Why do these flares affect Earth's ionosphere? And how does this impact our technology and daily life? By studying the effects of solar flares on the ionosphere's D and E layers, scientists can better predict communication disruptions and develop strategies to mitigate their impact. This knowledge is not only fascinating but also essential in our increasingly connected world. Geomagnetic storms and atmospheric ozone profiles. Our planet is enshrouded in a delicate layer of ozone, a molecule composed of 3 oxygen atoms, which forms a protective barrier in the stratosphere, absorbing harmful ultraviolet radiation from the sun. But this shield is not impervious. It is influenced by the complex interplay between geomagnetic storms and cosmic rays. Relationship between geomagnetic storms, cosmic rays, and atmospheric ozone. Geomagnetic storms are disturbances in Earth's magnetosphere caused by enhanced solar wind and interplanetary magnetic field conditions. These storms can alter the trajectories of cosmic rays, high-energy particles originating from outer space as they approach Earth. When cosmic rays collide with molecules in our atmosphere, they can initiate a cascade of reactions, one of which includes the formation of ozone in the lower stratosphere. The intensity of geomagnetic storms can affect the density and penetration depth of cosmic rays, which in turn influences the regional distribution of ozone production near the tropopause, the boundary between the troposphere and the stratosphere. This process is vital because ozone at this level significantly impacts the temperature and humidity of the tropopause, thereby affecting the overall planetary radiation balance. Changes in ozone density in the lower stratosphere. Recent studies have observed fluctuations in the ozone density within the lower stratosphere. These changes are critical as they can alter the amount of ultraviolet radiation that reaches the Earth's surface, with potential implications for both the environment and human health. The trends show an increase in ozone in the upper stratosphere, which is significant across various latitude bands, while non-significant negative trends have been noted in the lowermost stratosphere. Understanding these dynamics is crucial for predicting the effects of geomagnetic storms on atmospheric ozone and for developing strategies to safeguard our protective ozone layer. As we continue to explore these complexities, we not only deepen our knowledge of Earth's atmospheric processes but also enhance our ability to protect the delicate balance of our planet's climate system. Impact on spacecraft and satellites. High above Earth, beyond the protective embrace of our atmosphere, spacecraft and satellites orbit in a region where the sun's influence is direct and profound. Here, solar wind drivers, streams of charged particles ejected from the sun, pose significant risks to these human-made marvels. Risks to satellites from solar wind drivers. Solar wind drivers can dramatically alter the environment through which satellites travel. These charged particles, when arriving with sufficient speed and density, can heat the Earth's upper atmosphere, causing it to expand. This expansion increases the drag on satellites in low Earth orbit, potentially altering their paths and shortening their operational lifespans. Moreover, the solar wind's magnetic field can induce currents in satellites, which can disrupt their electronics and lead to system failures. Enhancements and losses of relativistic electrons in the outer radiation belts. The outer radiation belts, a region of space filled with high-energy particles, are particularly affected by solar wind drivers. These particles, including relativistic electrons, can be accelerated to nearly the speed of light. During periods of intense solar activity, the flux of these electrons can increase dramatically, posing a hazard to satellites. The enhanced levels of radiation can penetrate satellite shielding, damaging the sensitive electronics within. Conversely, certain solar wind conditions can also lead to the loss of these electrons from the belts, temporarily reducing the radiation risk. Understanding these space weather phenomena is crucial for the continued operation and reliability of our satellite infrastructure. By studying the effects of solar wind drivers and the behavior of the outer radiation belts, scientists can better predict and mitigate the risks to our vital technology in space. Predictive capabilities. In the quest to safeguard our technological society from the whims of space weather, scientists and engineers are developing advanced missions to predict the capricious nature of solar activity. These missions aim to provide a window into the future, offering a glimpse of the sun's behavior before its effects reach our planet. Potential of space weather prediction missions. The potential of space weather prediction missions is vast. By understanding the patterns and precursors of solar flares and coronal mass ejections, these missions could provide early warnings, allowing us to protect satellites, power grids, and astronauts from the adverse effects of space weather. The ability to forecast space weather with accuracy and lead time comparable to terrestrial weather forecasts would mark a significant milestone in our relationship with the Sun. Monitoring of solar wind properties and interplanetary magnetic field direction. Monitoring the properties of the solar wind and the direction of the interplanetary magnetic field (IMF) is crucial for predicting space weather events. The solar wind's speed, density, and temperature, along with the IMF's orientation, particularly its southward component, are key indicators of potential geomagnetic storms. Satellites positioned at strategic points, such as the Lagrange L1 point, a stable position between Earth and the Sun, continuously observe these solar wind parameters, providing real-time data that is essential for accurate space weather forecasting. As we continue to develop and refine these predictive capabilities, we not only enhance our ability to foresee and mitigate the effects of space weather but also deepen our understanding of the Sun's influence on our solar system. Space weather monitoring. In the realm of space weather, the ability to predict solar wind properties with accuracy is not a luxury, it's a necessity. The solar wind, a stream of charged particles released from the Sun, can have profound effects on Earth's magnetosphere, technology, and even our health. The need for accurate solar wind property predictions. Accurate predictions of solar wind properties are essential for mitigating the risks associated with space weather. For instance, knowing the speed, density, and temperature of the solar wind, as well as the direction of the interplanetary magnetic field, IMF, can help us prepare for geomagnetic storms that may disrupt satellite communications and power grids. The challenge lies in the solar wind's variability and the complex interactions it has with Earth's magnetic field. Real-time data and machine learning in space weather monitoring. The advent of machine learning has revolutionized space weather monitoring. By harnessing real-time data from satellites and ground-based observatories, machine learning models can learn from past events to predict future conditions. These models, including neural networks and gradient boosting algorithms, are trained on vast data sets to recognize patterns and make forecasts with increasing precision. For example, convolutional neural networks (CMEs) have been used to forecast solar wind speed by analyzing images from the Atmospheric Imaging Assembly (IA) and data from the Advanced Composition Explorer (ACE), located at the Lagrange L1 point. This approach allows for predictions that are not only accurate but also timely, providing essential information for space weather preparedness. As we continue to refine these techniques and integrate more real-time data, the potential for machine learning to enhance our predictive capabilities grows. This intersection of technology and science opens new frontiers in understanding and anticipating the whims of our star, the Sun. As we close this chapter on the Sun's influence over our planet, it's clear that space weather is not just a distant phenomenon occurring in the vacuum of space. It's a part of our lives, affecting everything from our satellites to our power grids. The Sun's activity shapes our technological and natural worlds in ways we are just beginning to understand. I invite you to continue exploring the fascinating world of space weather. There's a universe of knowledge waiting for you, and each discovery helps us better prepare for the Sun's next outbursts. The journey doesn't end here. Stay tuned for upcoming content where we'll delve deeper into the predictive capabilities of space weather forecasting. We'll explore how cutting-edge technology and research are opening new doors to understanding the Sun's temperamental nature and protecting our blue planet.